All right, so we have a lesson today talking about linear regression. We already talked about the equations of lines. Again, probably be a review, but you may not remember it. So oftentimes we want to be able to make conclusions or predictions about things. So we take data and analyze it. We'll do more of this in stats. Analyze data and draw some conclusions, and then maybe be able to come up with an equation that seems to fit the pattern of the data well. And then we can use that equation to make predictions as to what might happen in the future. So, a pediatrician would like to determine the relationship between infant female weights versus age. The pediatrician studies 100 newborn girls and finds their average weight at the end of 3-month interval. The data shown below. All right, so at age, when they're first born, they weigh 7.2 pounds on average. And then 3 months later, 12.2. And 6 months later, 15.1. So that's what the data say to us. And then we take this data and we actually plot it on a graph. So at 0, you're at 7.2. At 3, you're at 12.2 up here. So that's what this represents. When you look at the data, it looks very linear. It's not exactly a perfect line, but it is very linear. So we figure, hey, there's got to be a line that would help us predict, an equation or line that would help us predict pretty well what's going on here. So basically, in this beginning part, you're just going to take some kind of straight edge. So find a straight edge of some type. And you want to draw a line of best fit. So you want to fit as much data as you can and keep, a certain number above and a certain number below type thing. So I'm just going to start right at that point. I think that's a pretty good place to start. All right, so that looks pretty good. I got one above, one below. Pretty equal. All right, so that's mine. Now everybody's just not going to be exactly the same. Okay, it's you're eyeballing this. You're not actually calculating anything. All right, so we're just trying to fit it as best we can. All right, so this we would say is our line, or my line, that best fits the data. All right, so now we're going to pick 2 points that are on the line. They don't necessarily have to be data points, although it looks like I have 2 that are data points. So I could use those. Yeah, so I've got this one here for me. I've got this one and this one. They both happen to be on my line that I drew. So I'm going to use those. And from the data up above, that would be the points 0, 7.2 from the table up above. And it looks like the one that's 6, so 6, 15.1. And that came from the data up above. Okay, but if you hit like on a line somewhere like here, I guess I could have used 2, 10 based off of my line. That would have also been equation. So again, we might have a little bit different equations. So it says determine the equation. Okay, so this is what we did. This is what we did the other day. We need to find the slope. Since I have a y-intercept, I could use that y equals mx plus b format. Because I already have the y-intercept, so I already know b is 7.2. And then I can find the slope. So slope, we said, equals delta y over delta x, change in y over change in x. So 15.1 minus 7.2 over 6 minus 0. To change my slope, if I put that in, 15.1 minus 7.2 in your calculator would give you 7.9, and then over 6. And then if I put that in my calculator, looks like I'm getting 1.316 repeating. And it says round coefficients to the nearest 10. So y equals 1.3x plus 7.2 would be my equation for the line of best fit based off of my data. And yours might be a little different, so you could do that on your own. And then it says using your, so now we're going to let our calculator do the work for us and see if it comes won't be exact to ours, but we're gonna see what it comes up with for a line of best fit. So, how do we do that? So if you go to your calculator, we need to be able to enter our data. Look at my table, and go to my calculator. And I don't remember, but you have a stat key, which is right here, and that's where your table is gonna be. So if I hit stat, and then under edit, up here under edit, so I'm on the right spot, hit enter, and it gives me a table. Now you may or may not have things filled into your table. So for me, I'm gonna go up and clear it because I have stuff in there, so if I slide you up and I highlight over L2, don't hit delete. If you hit delete, you're gonna clear the whole row out. I don't want that, I just wanna clear what's in the list, so I hit clear, and then enter, and that clears the whole list. And then I can do the same thing on L1, clear, enter. Okay, so I've got clear lists to work with. And now I'm gonna enter the data that they gave me, that the doctor analyzed. So 0, enter, 3, enter, and so all the stuff in the X box, 6, enter. Your table in your note packet obviously is going across, but when you set up your table in your calculator, it goes down. So 0, 3, 6, 9, 9, you guys should all be typing this in, 9, 12, so you know what you're doing, and then 15 for my X values or my L1 list, and 7.2, and 12.2, and 15.1, 19.4, 21.5, and 26.3. Alright, so all my data is entered. And now I want the calculator to do some calculations for me. So if I go back to stat and over to where you see calculate, then there's a whole bunch of things it can do. And if you look at the fourth one down, that is your regression. That is your linear regression, or your line of best fit. So I'm going to hit number 4. And it's going to ask me what list your data is in. So mine are in list 1 and list 2, but let's say it wasn't. So just so, I don't know if everybody's calculator has all that in there, or if you even entered it in list 1, list 2. So you have all these L1s, look down here, L1 is in blue over 1, L2. So let's just say, I'll just fix it here, that this one was L3. So right now it's L3, but I need it to be L1. So what I did was I highlight over that, and then I hit blue key, and then I go to number 1, and now it fills in L1 for me. So just make sure you got the right list for the computer to look at. Don't have anything in the frequency list. Don't have anything in store regress. Okay, so we're just going to move down, enter, enter. And then it does the calculations for me. So there's my calculations, and it gives it to me in that y equals mx plus b form. So they tell me to round to the nearest tenth, so 1.2 and 7.8 for my final equation. Alright, so my A value, rounded, the nearest tenth, 1.2, and my B value, rounded to the nearest tenth, is 7.8. So my linear regression equation is y equals 1.2x plus 7.8. The nearest 10. Alright. Use your calculator to determine the linear correlation coefficient and round to the nearest 1,000. Alright, your correlation coefficient is your R value. There's an R value. Now, normally, well, some of you might in your calculator have gotten what you see up here on mine, but you also might have had R and R squared down here and all that things. And that's what I'm missing. So if you already have that, you already can see what your correlation coefficient is. But I don't have mine, which means I have to turn on stat diagnostic. So if you don't see it right now, you need to go to mode, which is next to second. And then down your list, you should see mine right here, stat diagnostic. Mine happens to be off, so I want to turn that on. So if you cleared your calculator, done some things, it'll turn off every time you clear your calculator. Highlight over on, hit enter, and now if I go back and redo, it's not going to fix it for me automatically, but if I go back to stat, and over to calculate, and back down to number 4, like we just did, list 1, list 2, enter, enter, enter. Now all of a sudden there's these R and these R squared values. And we are looking at our R value. And this is going to be a very high correlation because it's very close to 1. I think of it like as like a percentage, like 99.5% of your data fits on that line perfectly. Then it's a really, really strong correlation between the data and your equation. So if this number was, more like 50% of your data, then the correlation is definitely not as strong. Now, this number can also be negative. That's okay, because the negative, if it was negative 0.995, all that means is it's still 99.5% of your data that is basically on the line, and it's a high correlation, but the negative just means it has a negative slope. So that's not really going to affect it. So we would say, I'm going to round this to round to the nearest thousandth. Okay, so my R value to the nearest thousandth. And the nearest thousand. So R equals thousandths. And we said, we would say this is a strong positive correlation. It just means as they go up in age, their rate also increases. That's your positive correlation. So the age and rate have a strong correlation. Using the equation of best fit found in part C, so y equals 1.2 x plus 7.8. We're using that. Find the x-intercept. And we said if we're finding an x-intercept, we want to know where y is equal to 0. So that would be negative 0.78 equals 1.2x. Divide negative 7.8 divided by 1.2. Negative 6.5. Negative 6.5 comma 0 would be, using that equation, would be the x-intercept. But now it says, does this value apply to this problem? Why or why not? Well, clearly that makes no sense in this problem because you wouldn't say that somebody was negative 6.5 months old. So you would say, you would use it, like the x-intercept doesn't mean anything in terms of this problem. So it does not apply because x represents age. And this does not make sense in this particular problem. Alright, so just answering different things about the questions. Alright, keep going. Using the equation that your calculator produced in exercise 1, okay, so back to that equation. That's 1.2, so we'll all have the same thing. Predict the weight, so y equals 1.2x plus 7.8. That was the equation we got with our calculator. And so this is saying predict the weight of a baby girl after 10 months. Okay, so 10 months. Does that represent X or does that represent Y? That's what we're talking about, right? And if we look back at our table, that represents months or age was your X value, right? So if you have the equation, you have the X value, you should be able to find the weights. So Y equals 1.2 times 10 plus 7.8, which means if I type that in my calculator, that I'm getting approximately 19.8 pounds. So that particular weight, if you go back and look at your table at that age, 10 months was not actually on our chart, right? So we used the equation to help us make a prediction as to at 10 months how much the baby would weigh. And because our value that we're looking for, 10 months, is within the range of the values of data that we actually have, we feel pretty good that that prediction is going to be accurate. And we call that interpolation. Okay, if we are picking values to predict that are within the range of our data, then we say that is interpolation. That word right there. So we interpolate it. If we are looking for something that's outside the realm of our data, then we may not be quite as accurate because we don't know that it actually stays as linear as it did within the range. So we might not be as accurate, and that is called extrapolation when you are outside. But anyways, those are the two words. Extrapolation means that you are making a prediction using numbers that are outside of your data range, and interpolation means you are within your data range. So let's see, number 3. Using the equation that your calculator produced, okay, so same equation we used before, y equals 1.2 x plus 7.8. Predict the weight of a baby after 2 years. Okay, well, first of all, it's 2 years, and we need months to even use this equation. So we know that 2 years times 12 says that's 24 months worth of time. You can't put in 2 years in this equation because x is representing months for us. So y equals 1.2 times 24 plus 7.8. And we are predicting that after 2 years, your baby will weigh approximately 36.6 pounds. And we would say this is extrapolation because 24, if you go back and look at your data, 24 months was not something that when we plotted it, we could see was definitely linear. Like out of 24 months, maybe it curves way up. You know, way up over here, just kind of like a fluky thing. We don't really know what happens. We're just assuming it will continue in this pattern. So extrapolation, although used as a prediction, because you got to have some way to predict, might not be quite as accurate. So that's why you have your two different terms. But we're hoping it is, so that's what we use for interpretation. All right, so another one here. Your biologists are trying to create a least squares regression equation. Well, that's just a fancy way of saying line of best fit, relating to the length of steelhead salmon to their weight. So you got the length of each of your salmon and their weight. Determine the least squares regression, line of best fit, in the form y equals ax plus b for this data. Round all coefficients to the nearest hundredth. Okay. So you can stop this for a minute. You should be able to plug this in the calculator, and then you can turn me back on when you're done plugging this in. This is basically the same stuff we've done. Or if you think you don't remember how to do it, I guess you can just follow along. So your choice. All right, so I'm back. If you turned me off or you didn't turn me off, I'm back. So you would have gone to Stat and Edit, and here's your list. It's a little quicker, I hope you remember. Slide over, clear your list. And I'm entering the data they gave me, so 22, 24, 28, 34, 29, 42, 22, 3.43 pounds, 4.46 pounds, 7.08 pounds, 14.21 pounds, 22.19 pounds, 31.22 pounds, and 35.67 pounds. Okay, so all my data's in, and they want that equation. So where'd we go? Went to stats, calculate, number 4. This one, let's do is where I want it, no other things in there. Go down, calculate, and my R's and everything in there. They want me to round to the nearest hundred, so 1.33 and negative 27.98. So y equals 1.33x minus 27.98. Alright, that would be my linear equation, or line of best fit. Using the equation for part A, determine the expected weights. Alright, so all I gotta do is look at my chart. The expected weight is the y value, and 30 inches is the length. So y equals 1.33, length is 30, minus 27.98. And if I type that on my calculator, you should have gotten 11.92 pounds. Okay. Alright, using your equation from part A, determine the expected weights of a salmon. Okay, so now I'm looking for the weight. If it's 52 inches long, actually it's 8 inches again, right? So y equals 1.33, 52 minus 27.98, y equals 41.18 pounds. Answer. All right, what's this one say? In which part, B or C, so what I did up here or what I did there, did you use interpolation, and in which part did you use extrapolation? So interpolation, again, is you inputting data that is within, or inputting a number that's within your data range. So 30 inches is within the range, so it's probably going to be pretty accurate. That would be interpolation in here. Whereas the 52 is out here, and things could change after they get out here. This data seems like it makes a very linear pattern. So B is interpolation because 30 inches falls within 22 to 48, which is your table. And C is extrapolation because 52 inches is outside. Alright, so that's it. You should have time, because it didn't take me the full time to do this video, so I'd assume you have time. So please get your homework started on page 23 and 24, and I will see you tomorrow.